Hey everyone, and welcome to another deep dive. Today we're going to be taking a look at this book, Programming Quantum Computers.
Oh, very cool.
And we're going to be talking about how to actually program
Right.
these quantum computers, right? It's like having a superpower.
It is.
If you can harness quantum mechanics to solve problems,
It is.
that would take a regular computer just like years and years to figure.
Absolutely. And I think what's really neat about this book is that it's focused specifically on the programming aspect of it.
Right.
Not on the physics of actually building
Okay.
a quantum computer.
So we don't have to be
Yeah.
quantum physicists to...
No, not at all.
Okay, good.
Yeah, you can think of it kind of like you have your normal CPU in your computer, and now we're adding like a quantum processing unit or a QPU.
Right.
And it's a coprocessor. Like you might add a graphics card to your computer
Right.
for a specific task.
Gotcha. Okay. So
Yeah.
that makes sense. But, the word quantum scares a lot of people off.
Yeah. What's like the most fundamental idea that we need to
Sure.
grasp to start programming these things?
Well, it all begins with the qubit. And this is the fundamental building block of quantum computing,
Okay.
much like a bit is in classical computing.
Mm.
But the really cool thing about a qubit is, unlike a bit, which can only be a 0 or a 1, a qubit can be both at the same time, with some probability of being measured as either one.
What?
Yeah.
How is that even possible?
That's the idea of superposition.
Okay, so it's like a coin that's spinning in the air.
Yeah.
Before it lands on heads or tails.
That's a great analogy.
Okay, but how does that actually help us compute anything?
Well, imagine you're trying to simulate a complex molecule. Okay, with classical bits, you'd have to represent each possible configuration of that molecule separately.
Right.
But with these qubits being in a superposition state,
Okay.
you can represent all of those different configurations at the same time
Oh, wow.
and explore many possibilities simultaneously. So that's where the power comes
That's
in.
where the power comes in, exactly.
Okay, I see that. All right, well, the book mentions something called like magnitude and relative phase
Right.
when it's describing these qubits.
Yeah.
What is that all about?
So think of a qubit as like a wave.
Okay. Right.
And it has a certain amplitude and phase, and the magnitude is telling you how much 0 and 1 is mixed into that superposition state.
Gotcha.
So like how high that wave is.
Okay.
And the relative phase is kind of like a time delay between those two parts of the wave. So by controlling both of those things, the magnitude and the relative phase, we can manipulate the qubit
Right.
and perform calculations.
Okay. It kind of sounds like mixing audio.
Yeah.
Like two tracks together where you're adjusting the volume of each one.
Right. And the timing.
Yeah, and the timing, and
That's
that
what it would create.
creates like, different effects. So we're kind of like composing these algorithms by
Exactly.
adjusted.
Great analogy.
Oh, okay. All right, cool.
Yeah.
So one of the applications of that is the ability to generate truly random numbers.
That's right.
Wait, hold on a second. I thought computers were already good at
Yeah.
generating random numbers.
So this is something that a lot of people think. But the reality is that classical computers rely on algorithms
Okay.
to produce what are called pseudo-random numbers.
Okay.
Okay? So they may seem random,
Right.
but if you know the algorithm, you can actually predict them.
Right.
QPUs, on the other hand, can leverage these quantum phenomena to create true randomness.
Okay, so why is true randomness so important?
Well, there's lots of applications for it.
Okay.
But one of the biggest ones is in the field of cryptography.
Mm-hmm.
Imagine trying to encrypt your financial transactions with a key
Okay.
that was generated by truly random processes on a quantum computer.
Right.
That level of security would be practically unbreakable with classical computers.
Oh, wow. Okay.
Yeah.
So this could literally reshape how we think about
Absolutely.
online security.
Absolutely. And this is really just the beginning.
Okay.
We're talking about single qubits right now.
Right.
The real magic starts when we start to entangle multiple qubits together.
Okay. Entanglement. Now, that's
Yeah.
a word that gets people talking.
Yeah. Well,
What makes it so special?
It's a very strange phenomenon. Imagine having two qubits that are linked
Okay.
in such a way that their fates are intertwined.
Okay.
You measure one qubit and instantly the state of the other,
Wow.
no matter how far apart they are. It's like they're communicating faster than the speed of light,
Really?
but without actually exchanging any information.
So is that is that like just a theoretical curiosity, or
Yeah.
can we actually like do something with it?
Entanglement is actually a fundamental resource for quantum computing. It's the key ingredient in applications like quantum teleportation and superdense coding,
Hold on.
where we can transmit information in ways that are impossible classically.
Quantum teleportation, are we talking about like beaming people?
Yeah.
Like in Star Trek?
Not quite.
Okay.
We're talking about teleporting the information
Oh, okay.
and get encoded in a qubit.
Right.
So it's like setting a blueprint that allows someone to perfectly recreate an object on the other side,
Right.
but without physically sending the object itself.
Gotcha. Okay.
Yeah.
That makes sense.
Yeah.
All right. And so the book says that we can actually try this
Yes.
using IBM's
Yeah.
5-qubit quantum computer.
Yes. In fact, programming quantum computers provides code that you can run to teleport a qubit yourself
Wow.
using a language called OpenQASM,
Okay.
which is supported by IBM's Quantum Cloud platform.
So I can literally teleport a qubit.
Yeah.
It's sitting in a lab across the world.
Yeah, it's pretty remarkable.
This is getting real now.
It is, yeah. It's a remarkable example of how quantum computing has moved from theory to practice.
Yeah.
And this is still really just scratching the surface.
Right.
We've only just begun to explore the potential of quantum computing.
Well, I am definitely hooked.
It's-
I can't wait to see what other mind-bending concepts
There's a lot more.
we find in this book.
There's a lot more to discover.
Yeah.
Next time we'll dive into how QPUs can perform calculations directly on quantum superpositions,
Okay.
which opens up a whole new world of possibilities.
All right. Quantum arithmetic, here we come.
That's right.
All right. So last time we kind of left off right at the edge of our seats, ready to jump into this quantum arithmetic.
Yeah, quantum arithmetic.
So how do we crunch numbers with these qubits?
It's interesting because much like, classical computers use bits to represent numbers, we have quantum integers, which are built from qubits.
Okay.
But instead of having like a fixed value,
Right.
a quantum integer can represent all possible values at the same time.
What? Thanks to superposition. Okay, but how do you add or subtract or anything when you have this like blurry mix of possibilities just like swirling around? Like, how do you even do math?
It's more structured than you might think.
Okay.
Imagine a simple operation, like just incrementing,
Okay.
right? Adding one to a value.
Okay.
In programming quantum computers, they talk about using these special quantum gates,
Okay.
specifically multi-conditioned CNOT gates, to kind of mimic that add and carry operation that you would do in classical arithmetic.
Okay.
But what's cool is those operations happen
Yeah.
to all the possible values within that quantum integer at the same time.
So it's like parallel processing, basically,
Exactly. It's like massive parallel processing.
across all the potential values that are in the superposition.
That's where the speed up comes from.
Okay. All right. So it's not just simple addition.
Yeah.
And the book also shows
Right.
how to add two quantum integers together.
Yeah, you can actually create a circuit that looks very similar to a classical adder circuit.
Wow.
But instead of using like your typical logic gates,
Yeah.
you're using these CNOT gates.
Okay. Can we also like do logical operations?
Yes, you absolutely can.
Like AND and OR and all that?
Yeah, so,
With qubits.
you remember the CCNOT gate we talked about before?
Yeah.
Well, that essentially acts as a quantum AND gate.
Oh, okay.
It'll only flip that target qubit
Uh-huh.
if both of the control qubits are 1.
Okay, so it's kind of like the quantum equivalent of those
It's exactly
logic gates that we all learned in,
That's right.
intro to programming.
Intro to programming, exactly.
So we can build complex operations just by
Yeah, you can string together these CCNOT gates
stringing them together.
to implement more complex logical operations.
Okay.
And from there, you can build quantum versions
Yeah.
of other familiar gates,
Yeah.
like the XOR gate. Yeah. So we can build this whole quantum toolbox from these fundamental building blocks.
It's like we're hacking the universe.
Yeah.
With logic gates.
It's really quite amazing.
All right, so
Yeah.
there's got to be some catch, though, right? Like, there can't be all sunshine and rainbows with quantum computing.
One of the fundamental rules of quantum mechanics is that operations have to be reversible.
Reversible?
Yeah. Every action has to have an undo button.
So, like, curl plus Z in a text editor.
Exactly.
Okay, but why is that so important in the quantum world?
It's about preserving information.
Okay.
Okay. At the microscopic level, physical processes are reversible.
Right.
Okay. To accurately simulate those processes, on a quantum computer.
Okay.
Our actions need to be reversible, too.
So it's like a game where you can't, like, destroy any of the pieces. You can only just rearrange them or something.
That's a good analogy.
Okay, does that make designing these quantum programs, like, extra tricky?
Well, it does require a shift in thinking. You know, imagine, for example, you're calculating the absolute value of a quantum integer.
Right.
You can't just discard the sign information.
Okay.
You have to store it somewhere.
Okay.
And there's a technique called uncomputation for doing this.
Uncomputation. So it's just like a fancy word for undoing something?
Well, it's more than just undoing it. It's about carefully reversing the computation
Okay.
to restore the original state of the qubits,
Okay.
except for the desired output.
So you're like cleaning up after yourself.
That's a good way to put it. Yeah, you're tidying up,
Okay.
and you're leaving just the result that you need.
Okay. All right. So it's like the quantum equivalent of Marie Kondoing your code.
Yeah, I like that analogy.
Okay. So
Right.
everything has its place. You don't
Right.
just throw things away.
Right.
All right. So this leads us to a very powerful concept called amplitude amplification.
Yeah, that's a really important one.
I remember that from when the book was talking about
Yes.
quantum search algorithms.
Right.
What is the big deal with amplitude amplification?
So you remember how measuring a qubit collapses its superposition?
Mm-hmm.
Amplitude amplification is a clever technique for manipulating the probabilities within that superposition,
Okay.
to boost the chances
Okay.
of getting a specific answer that we're looking for.
So instead of just getting like a random outcome, you can kind of nudge those quantum dice.
Exactly. You're nudging the dice.
In your face.
You're loading the dice. Yeah.
Okay. All right. So it's kind of like searching for a file on your hard drive, like
Yeah.
a specific file.
Yeah.
And it's a really messy hard drive.
Totally.
And amplitude amplification is kind of like,
It helps you prioritize the files you want,
okay.
right?
All right. So it brings it to the top of the search list.
Exactly.
Okay.
Yeah, it's a good analogy.
So how does it actually work, though? Because I'm a little fuzzy on the mechanics of it.
Yeah.
The book mentions a marked value.
Right.
What is that?
So the marked value is simply the answer you're looking for,
Okay.
right? The solution to the problem you're trying to solve.
Gotcha.
And amplitude amplification works by first marking this value
Okay.
with a phase flip.
Hold on, a phase flip.
Yeah.
Isn't that like messing with this delicate quantum information?
Well,
Yeah.
it is, but in a very controlled way.
Okay.
So by strategically flipping phases
Okay.
and then applying a specific sequence of operations,
Okay.
including something called the mirror operation,
Right.
we can actually transform those phase differences into magnitude differences.
Okay.
It's like you're taking a very faint whisper and amplifying it
Gotcha.
into a shout.
So we're basically harnessing the quantum weirdness to make the solution pop out
That's a good way to put it.
more clearly when
Yeah.
we measure those qubits.
You got it.
Okay.
Huh?
Can we use it to solve like any problem or?
Oh, the key to using amplitude amplification effectively
Yeah.
is having a way to mark that desired solution
Okay.
with a phase flip. And that's where quantum search algorithms come in.
Right.
They provide clever ways to encode the solution to a problem as a phase difference.
Okay.
And that sets the stage for amplitude amplification.
So these quantum search algorithms are like specialized tools
They,
for highlighting the needle in a haystack.
that's a good way to put it.
And this is where Grover's algorithm comes in.
Exactly. Grover's algorithm is a classic example.
Right.
It's designed to search unsorted databases,
Okay.
which is a problem that plagues classical computers.
Right.
Imagine trying to find a specific contact
Yeah.
in a giant phone book
Yeah.
with no alphabetical order.
Ouch. That sounds terrible.
Yeah, it's a nightmare.
So instead of flipping through every page, Grover's algorithm uses amplitude amplification to kind of like zoom in.
Exactly. Yeah, it zooms right in.
Right contact.
Yeah.
Okay.
And it does so with a significant speed up
Wow.
compared to classical methods.
So we're not just talking about theoretical concepts here. We're talking about algorithms that can have a real impact
Right.
on how we solve
Yeah.
practical problems.
Absolutely. And as the field progresses, we're going to find even more applications for these algorithms,
Yeah.
from optimizing complex systems to speeding up machine learning.
Okay, cool.
Yeah.
So there was one other concept that came up in this whole amplitude amplification section, the quantum Fourier transform, or QFT.
QFT.
What's that all about?
So the QFT is like a secret weapon for analyzing quantum states.
Okay.
Remember how we talked about these states being a superposition of different values,
Right.
each with a specific magnitude and phase?
Right.
Well, the QFT is this mathematical operation
Okay.
that helps us reveal hidden patterns within those superpositions,
Okay.
particularly ones that relate to periodic signals.
Periodic signals like repeating patterns.
Exactly, repeating patterns in the data.
In the data, okay, I can see how that might be useful, but how does it actually, like, uncover those patterns?
So the QFT involves this sequence of carefully choreographed Hadamard and controlled phase gates.
Right.
Okay. And these gates transform the quantum state in a way that allows us to pick out its frequency components.
Okay.
And the book visualizes this beautifully using circle notation.
Yeah, I remember those diagrams with all the circles representing the magnitudes and phases.
Yeah, and by following those circles through the QFT process, you can actually see those frequencies emerge.
So it's like taking a really complex sound wave and breaking it down into its...
You're like a spectrum analyzer.
Yeah.
Yeah, you're breaking it down into those individual frequencies.
Right.
And you can see the hidden harmonies within the music.
Okay, so if I'm understanding this correctly, we can actually combine the QFT with the amplitude amplification.
And that's a very powerful combination.
To target and amplify
specific frequencies.
Frequencies within a
quantum state.
It's like a quantum equalizer.
That's a great analogy.
Okay, and this is how Shor's algorithm works.
This forms the backbone of some of the most celebrated quantum algorithms.
Right.
Including Shor's algorithm.
Yeah, that's the one that can, like, crack the encryption that protects our online world.
That's the one. Shor's algorithm is this groundbreaking example of how quantum computing can solve problems that are considered virtually impossible for classical computers.
So we went from adding quantum integers to, like, breaking the internet.
That's right. Like, we've covered a lot of ground.
It seems like every time we dig deeper into this quantum computing, the possibilities just get more and more mind-blowing.
You're telling me, and we're just getting started, there's a whole universe of applications waiting to be explored.
Yeah.
From quantum machine learning to simulating the behavior of molecules and materials.
Okay, well, consider me officially intrigued.
Good.
Yeah.
I can't wait to see what other wonders await us in the final part of this.
There are many.
Quantum adventure.
Yeah, we've got a lot more to cover.
Welcome back. It's amazing we've already made it to part 3 of our deep dive into programming quantum computers.
Yeah.
So far, we've teleported qubits, explored Shor's algorithm, and now I'm really curious about, real-world applications. Yeah. Like, what can we actually do with these quantum computers today?
Well, it's an exciting time because we're seeing a lot of those theoretical concepts start to blossom into practical applications.
Okay.
One area that's generating a lot of buzz is quantum machine learning.
Oh, wow. So we're taking machine learning, which is already a hot topic, and adding quantum to it.
Exactly.
Okay, I'm intrigued, but I'm also a little intimidated.
Yeah.
How does quantum mechanics make machine learning even more powerful?
Well, it's not always about raw power, but about tackling problems that are simply out of reach for classical machine learning approaches.
And quantum algorithms can exploit those unique properties that we've been talking about to provide solutions that are exponentially faster for certain tasks.
Exponentially faster. So we're talking like solving problems in hours.
Intentionally, yeah.
That would take a classical computer centuries to solve.
In some cases, yes.
Wow. Okay. Give me an example.
Well, the book talks about the HHL algorithm, which focuses on solving systems of linear equations.
That sounds a bit dry.
It might sound dry, but it's a cornerstone of many machine learning techniques.
Okay.
From, finding the best fit line through data points to training complex neural networks.
Okay, so instead of like crunching through massive data sets for weeks on end, we could potentially use this HHL algorithm.
Yeah, you could use the HHL algorithm.
And get the same result.
Much faster.
In a fraction of the time.
That's the idea.
Okay, and the book also mentions something called quantum principal component analysis.
QPCA.
Or QPCA. What's that all about?
So imagine you have a data set with just a ton of features or variables.
Okay.
Making it really complex to analyze.
Right.
QPCA, like its classical counterpart PCA, helps you identify the most important features to reduce that complexity without losing any of the crucial information.
So it's like decluttering the data before you feed it.
That's a good way to put it.
To a machine learning algorithm.
You're simplifying it.
Okay.
To make it more manageable.
Does the quantum version offer any advantages there?
Absolutely. QPCA can potentially perform this dimensionality reduction significantly faster than classical PCA, especially for really massive data sets.
So it's like finding the signal in the noise, but with a quantum magnifying glass.
Yeah, that's a good analogy.
Okay, so quantum machine learning this isn't just hype. It has the potential to actually revolutionize
Yeah, it's not just hype.
how we analyze data and
It's early days, but
build
the potential is there.
intelligent systems. Okay. The book also touched on quantum support vector machines, or QSVM.
Yeah, QSVMs.
What's the quantum twist on that?
Well, QSVMs draw inspiration from their classical counterparts,
Okay.
which excel at these classification tasks,
Okay.
like distinguishing different categories of objects or data points.
Right.
Imagine trying to separate photos of cats and dogs.
Right.
A classical SVM would learn a boundary to divide those two categories.
Gotcha. So the quantum SVM is going to use quantum mechanics to define that boundary
That's the basic idea.
between those cute furry faces.
Yeah, you got it.
Okay.
So, like we've seen with other quantum algorithms, QSVMs offer that tantalizing possibility of an exponential speedup
Okay.
for certain classification problems.
So it feels like we're like standing on the precipice of a quantum revolution here,
It does feel that way.
with all these algorithms ready to transform everything from like medicine to finance to AI.
The excitement is definitely palpable, and I think programming quantum computers does a fantastic job of bridging that gap between the theoretical and the practical,
Right.
providing a roadmap for anyone who's eager to explore this emerging field.
I totally agree. This deep dive has been an incredible journey.
Yeah, it has.
And I feel like I'm walking away with just a sense of awe.
That's the beauty of quantum computing.
I'm like,
It sparks a sense of wonder.
yeah, a thirst to learn more.
And who knows, maybe one of our listeners will be the next pioneer
That's awesome.
to unlock even more incredible possibilities.
Yeah. So to everyone listening, if this deep dive has piqued your curiosity, definitely check out Programming Quantum Computers.
Yeah, good book.
And, embark on your own quantum adventure. The future is waiting to be written, and maybe, just maybe, it'll be written in quantum code.
I like that.